NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math tutorial. Today, we'll solve the expression 1/3 minus 2x times 1/3 minus x following a specific algorithm. Let's look at our example. We need to expand the product of the binomials 1/3 minus 2x times 1/3 minus x. Let's start with step 1. We'll use the general product formula for two binomials, which states that a plus bx times a plus cx equals a squared plus the quantity bx plus cx times a plus bx times cx. This formula helps us organize our work. In step 2, we'll substitute the values from our problem into the formula. In our problem, a equals 1/3, b equals -2, and c equals -1. So we get 1/3 minus 2x times 1/3 minus x equals 1/3 squared, plus the quantity -2x plus -x times 1/3 plus -2x times -x. For step 3, we'll compute each term in our expression. 1/3 squared equals 1/9. -2x plus -x equals -3x. And -2x times -x equals +2x squared. So our expression becomes 1/9 plus -3x times 1/3 plus 2x squared. In the final step, we'll simplify and combine like terms. When we distribute -3x times 1/3, we get -x. This gives us our final answer, 1/9 minus x plus 2x squared. We need to expand the product of x squared minus 3 times x squared minus 5. To solve this, we'll use the common term identity. This identity tells us that when we have two binomials in the form a plus b times a plus c, we can expand it as a squared plus a times the sum of b and c, plus the product of b and c. In other words, a plus b times a plus c equals a squared plus a times the quantity b plus c times c. In our case, x squared is our common term, a, -3 is b, and -5 is c. Now, let's apply the identity. We get x squared squared, which is x to the 4th power, plus x squared times the sum of -3 and -5, plus the product of -3 and -5. Let's simplify this expression. X squared squared is x to the 4th power. The sum of -3 and -5 is -8, and the product of -3 and -5 is +15. So our expanded expression is x to the 4th power minus 8x squared plus 15. Let's move on to our second example. Here we need to expand the product of 3x squared minus 7 times 3x squared plus 11. We'll use the same common term identity for this problem. In this case, 3x squared is our common term, a, -7 is b, and +11 is c. Now, let's apply the identity. We get 3x squared squared, which is 9x to the 4th power, plus 3x squared times the sum of -7 and +11, plus the product of -7 and +11. Let's simplify this expression. 3x squared squared is 9x to the 4th power. The sum of -7 and +11 is +4, and the product of -7 and +11 is -77. So our expanded expression is 9x to the 4th power plus 12x squared minus 77. Let's summarize what we've learned. When expanding products of binomials with a common term, we can use the common term identity to make our work easier. We identify the common term, and then apply the formula a squared plus a times the sum of b and c, plus the product of b and c. This approach is particularly useful when both binomials share a common term, as it allows us to expand more efficiently than using the distributive property directly. Practice applying this identity to different binomial products to become more familiar with it. We have the expression 1 plus 2a times 2a minus 1 times 4 squared plus 3. Let's solve this step by step following the algorithm shown. First, we'll work with the first two parentheses. We can rewrite this as the expression 2a plus 1 times 2a minus 1 times 4 squared plus 3. Now, we can recognize that 2a plus 1 times 2a minus 1 is a difference of squares pattern, which equals 4 squared minus 1. So our expression becomes 4a squared minus 1 times 4 squared plus 3. Next, we need to apply the common term identity shown in our algorithm. The common term identity states that a plus b times a plus c equals a squared plus a times b plus c times c. In our case, a is 4 squared, b is -1, and c is 3. Applying this identity, we get 4 squared squared plus 4 squared times -1 plus 3 plus -1 times 3. Now let's simplify this expression. We get 16a to the 4th power plus 2 times 4 squared plus -3, which gives us 16a to the 4th power plus 8 squared minus 3. Now, let's move on to our second example. We have the expression 2 minus 1 squared times 2 plus 1 squared times 4 squared plus 2 squared. Let's follow the same algorithm. First, we can rewrite this expression as 2 minus 1 times 2 plus 1 times 4 squared plus 2, all squared. Next, we recognize that 2 minus 1 times 2 plus 1 is another difference of squares, which gives us 4 squared minus 1. So our expression becomes 4 squared minus 1 times 4 squared plus 2, all squared. Now, we'll apply the common term identity again. In this case, a is 4 squared, b is -1, and c is 2. Applying the identity, we get 4 squared squared plus 4 squared times -1 plus 2 plus -1 times 2, all squared. Let's simplify what's inside the square. We get 16a to the 4th power plus 4 squared minus 2, all squared. Now, we need to square this expression. For this, we'll use the formula for the square of a sum, which states that the square of a plus b plus c equals a squared plus b squared plus c squared plus 2, a b plus 2, a c plus 2bc. In our case, a is 16a to the 4th power, b is 4 squared, and c is -2. Applying the formula, we get the square of each term plus the cross products. Finally, let's simplify this expression. We get 256a to the 8th power plus 16a to the 4th power plus 4 plus 128a to the 6th power minus 64a to the 4th power minus 16 squared. Combining like terms, our final answer is 256a to the 8th power plus 128a to the 6th power minus 48a to the 4th power minus 16 squared plus 4. We need to solve the expression 2 minus 5 times 2 minus 1 times 4 squared plus 12 minus 5. We'll solve this step by step using the common term identity. First, let's recall the identity we'll be using. For expressions a plus b times a plus c, this equals a squared plus a times b plus c times c. Now, let's start solving our expression. The first step is to rewrite the expression. We note that 2 minus 5 can be viewed as 4 squared minus 12 plus 5. This gives us 4 squared minus 12 plus 5 times 4 squared plus 12 minus 5. For the second step, we'll rewrite this to make the common term easier to see. We can express this as 4 squared minus the quantity 12 minus 5 times 4 squared plus the quantity 12 minus 5. For step 3, we can now apply the identity for the difference of squares. This gives us the square of 4 squared minus the square of 12 minus 5. For step 4, we'll expand these terms. The square of 4 squared gives us 16a to the 4th. And for the square of 12 minus 5, we get 144 squared minus 120 plus 25. For our final step, we simplify the expression by distributing the negative sign and combining like terms. This gives us 16a to the 4th minus 144 squared plus 120 minus 25. Now, let's move on to our second example. We need to solve the expression x cubed plus 1 times x cubed minus 1 times x to the 6th plus 5. Let's solve this step by step. First, we'll focus on the first two factors. We can apply the difference of squares formula to x cubed plus 1 times x cubed minus 1, which gives us x to the 6th minus 1. Now, we can apply the common term identity to the expression x to the 6th minus 1 times x to the 6th plus 5. Using the common term identity, we get x to the 12th plus x to the 6th times the sum of -1 and 5, plus the product of -1 and 5. Finally, we simplify the expression. X to the 6th squared gives us x to the 12th. The sum -1 plus 5 is 4, multiplied by x to the 6th gives us 4x to the 6th. And -1 times 5 is -5. So our final answer is x to the 12th plus 4x to the 6th minus 5. Let's summarize what we've learned. We've seen how to apply algebraic identities to simplify complex expressions. For the first example, we used the common term identity and difference of squares to simplify the expression to 16a to the 4th minus 144 squared plus 120 minus 25. For the second example, we applied the difference of squares and common term identity to simplify the expression to x to the 12th plus 4x to the 6th minus 5. Remember that identifying common terms is key to applying these identities effectively. With practice, you'll be able to recognize patterns and solve these problems more quickly. We need to expand the product of these two binomials, the quantity 3x squared y minus 4 times the quantity 3x squared y plus 7. To solve this, we'll use the common term identity. The rule states that for expressions in the form of a plus b times a plus c, this equals a squared plus a times the quantity b plus b times c. This identity helps us expand products where the terms have common factors. Looking at our expression, we can identify the parts. A is 3x squared y, b is negative 4, and c is positive 7. Now, we'll apply the identity to expand this product. Let's substitute these values into our identity formula. First, we find a squared, which is 3x squared y squared. Next, we compute a times the quantity b plus c. This gives us 3x squared y times the quantity negative 4 plus 7, which is 3x squared y times 3. Finally, we calculate b times c, which is negative 4 times 7, giving us negative 28. Simplifying, we get our final answer, 9x to the 4th power y squared plus 9x squared y minus 28. This is the expanded form of our original expression. Now, let's look at a second example. Here we have the product of xy minus 3y squared and xy plus 5y squared, with both expressions squared. We can simplify this by first recognizing that we have two squared binomials. Let's rewrite this as the square of the product of these binomials, the quantity xy minus 3y times xy plus 5y squared. Let's solve the inner product first using our common term identity. In this inner product, we can identify a as xy, b as negative 3y, and c as 5y. Now, we'll apply the common term identity to expand this inner product. We get a squared, which is xy squared, plus a times the quantity b plus c, which is xy times the quantity negative 3y plus 5y, giving us xy times 2y, or 2y squared x, plus b times c, which is negative 3y times 5y, giving us negative 15y squared. Collecting like terms in the inner expression, we get x squared y squared plus 2x, y squared minus 15y squared, all squared. We can factor out y squared from each term in the inner expression. This gives us y squared times the quantity x squared plus 2x minus 15, all squared. When we square this expression, we get y to the 4th power times the quantity x squared plus 2x minus 15 squared. To expand the remaining squared expression, we'll use the formula for the square of a trinomial. The square of a trinomial of plus b plus c is a squared plus b squared plus c squared plus 2, a b plus 2, ac plus 2bc. In our case, as x squared b is 2x and c is negative 15. Substituting these values into the formula, we get x to the 4th plus 4x squared plus 225 plus 4x cubed minus 30x squared minus 60x. Now, we collect like terms. We have x to the 4th plus 4x cubed plus 4x squared minus 30x squared minus 60x plus 225. Combining like terms, we get x to the 4th plus 4x cubed minus 26x squared minus 60x plus 225. Remember that this expression is multiplied by y to the 4th power. So our final answer is y to the 4th times the quantity x to the 4th plus 4x cubed minus 26x squared minus 60x plus 225. Distributing the y to the 4th, we get x to the 4th y to the 4th plus 4x cubed y to the 4th minus 26x squared y to the 4th minus 60x y to the 4th plus 225 y to the 4th. Let's recap what we've learned. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.